Halite, the crystal for protection. Quartz, the crystal for healing. Garnet, the crystal for passion. Now, which of these crystals is not like the others? It's quartz, because it can actually heal you. That's right, it can cure blindness, treat prostate cancer and uterine fibroids, even kidney and biliary stones. And the best part? It all comes from the crystal vibrations. Because quartz is piezoelectric. These vibrations occur when alternating current is applied to the crystal, causing it to rhythmically expand and contract. Well, so all crystals do technically vibrate. These vibrations are called phonons. Basically, the chemical bonds holding them together are kind of like springs. And assuming you're like me and you like to keep your crystals above 0 degrees Kelvin, the atoms will vibrate a lot from heat, and those vibrations will travel through the crystal lattice. But some crystals are special because their vibrations can be converted into electricity. And they can convert electricity back into vibrations. And quartz is one of them. And piezoelectricity is, in part, why this terrible candy glows when I bite on it. Because, and you're not gonna believe this, but sugar crystals are also piezoelectric. See my bonus footnote for Winto Mint fluorescent details. So that's cool and all, you might say, but now I've got a real problem. I was going to wear this massive piezoelectric topaz necklace to Coachella, but now I'm worried that if I get too close to the massive speakers and the bass drops, the sound waves will vibrate my crystal necklace and I might get electrocuted. And that would be like, not the vibe. That may or may not be a valid concern. Let's do some physics to find out. Let's try to better understand piezoelectricity. So when some liquids cool slowly, there's lots of time for all the molecules or ions to arrange themselves all into a nice low energy state called a crystal lattice. All the boring crystals, like garnet and diamonds, have a crystal lattice that is symmetric around a center, or centrosymmetric. Ugh, boring. But piezoelectric crystals are not symmetric around a center. When you apply mechanical stress, squeezing or stretching the crystal, you shift those ions, creating charge. That's the electric part. This displacement pushes the positive charges towards one face of the crystal and negative charges towards the other, creating external electric potential. What's cool is that this mechanical force to electric voltage can also effectively let you store physical force as digital data. Some microphones, especially contact mics, work this way. When sound waves enter the microphone, they hit a piezoelectric crystal diaphragm and cause it to compress in a way that generates electric signal. That signal can be stored as the data of the sound waveforms. This is called the piezoelectric direct effect. But, as I mentioned, you can also go the other way and convert electrical signals into physical vibrations. If you apply an electric field to the crystal, the internal ions will physically shift to align with that field. This causes the entire lattice to expand or contract. An example of this is a quartz watch. A quartz crystal is very precisely cut and positioned, such that when the circuit sends a pulsing signal, the crystal vibrates 32,768 times a second. A microchip then counts down, repeatedly dividing the number of vibrations in half, until it gets to exactly 1 per second, which ticks the watch hand forward. This electromechanical property is pretty useful, so piezoelectric crystals are all over the place. For example, the direct effect, physical force to electricity, can be found in cooking and cars. In a grill or oven gas igniter, pressing the button triggers a spring-loaded hammer that strikes the crystal. That in turn produces a high-voltage spark that ignites the gas. In some cars, during a crash, airbags use piezoelectric crystals to detect deceleration forces. It then sends that electric signal to deploy the airbag. The inverse effect, electrical signal to physical vibrations, is found in your phone. Some phones use piezo elements to vibrate the glass phone screen. The inverse effect is used a lot when you want very high frequency vibrations. For example, some humidifiers use the crystals to vibrate the water into a fine mist. And all those crystal healing health claims are also using the indirect effect. In phacoemulsification, or cataract surgery, a piezoelectric transducer vibrates to emulsify the cataract, allowing it to be removed. Prostate cancer and uterine fibroids are treated with a high-intensity focused ultrasound, where the piezoelectric transducer creates an ultrasonic wave that targets the tumor or fibroid. And kidney and biliary stones are broken up with extracorporeal shockwave lithotripsy.
Extracorporeal shockwave lithotripsy,
where a high-energy shockwave breaks up the stone. Now, it's nice to imagine for our auras that we're surrounded by nice shiny, reflective, fun crystals. But in practice, while quartz and other lattice crystals are piezoelectric, and are still used to some extent, what's more common these days are piezoelectric ceramics, like lead, zirconate, titanate, or PZT. What's the difference? Will these ceramics still meet my crystal needs? Well, crystals are a lot of unit crystals in a lattice structure, like this quartz. But technically, you can take a ton of tiny crystals and just kind of fuse them together at high heat. And this creation is called a ceramic. Pottery is an example of this. The clay is a slurry of very tiny crystals. When you fire your pottery, you don't actually melt them entirely. Instead, the intense heat causes the very edges of the crystals to melt and fuse together, a process called sintering. Pottery does contain quartz, but the reason it's not piezoelectric, like PZT, really comes down to crystalline orientation and ferroelectricity. In pottery, the quartz grains are randomly oriented, meaning their individual piezoelectric effects cancel each other out. But PZT is special because it's ferroelectric. Even though it's a solid ceramic, where the grains are fixed in place, it contains microscopic regions of uniform polarization, called ferroelectric domains. When a massive external electric field is applied, these domains are forced to flip and align in the same direction. This is called poling. Instead of canceling each other out, the microscopic polarization vectors align, creating a net macroscopic piezoelectric response. But if ceramics aren't pure and shiny enough for you, topaz and tourmaline are also piezoelectric. Side note, but I asked all my friends if they had any topaz or tourmaline jewelry I could, just look at, but they all wisely told me, no. Sorry. Cool. So let's get back to your Coachella concerns. At first glance, yeah, the sound waves hitting and compressing the massive topaz crystal on your necklace could cause it to discharge electricity. But assuming it did, would the bass drop be enough to electrocute you? Time for some very basic back of the napkin physics. First, we're going to say that your topaz necklace is actually quartz, because I found a lot more online about the piezoelectric constants of quartz than topaz or tourmaline. First, we need to calculate the force coming from the speakers. The decibels of the speakers could be around 100 decibels if you're standing close to them, but that's pretty bad for your ears, so be careful. You can use the sound pressure level equation to convert that into around 2 pascals. So now we can use the direct piezoelectric equation to calculate the shock. Voltage equals the piezoelectric constant times the stress in pascals times the thickness of the crystal. So for a 1 centimeter thick crystal, we get 1 millivolt of voltage. Your skin is actually really good at insulating, so we would need more like 30 to 50 volts for you to actually feel anything. Luckily, you're probably pretty sweaty at the concert, and sweat lowers the resistance of your skin to maybe 5 volts. Unfortunately though, we're just not gonna get to 5 volts from sound waves, because sadly, it turns out that the acoustic impedance of quartz is actually very high. So the sound waves are just gonna bounce off. Not to mention, the force is really hydrostatic stress. But don't worry, you might accidentally get checked by someone in the mosh pit, which I'm assuming that they definitely have at Coachella. And while we're assuming you got violently moshed, such that the necklace hits your chest and you reflexively reach up to grab it as it lands, completing the circuit, let's also assume that your necklace is stylishly massive, like a 10 centimeter cube. Now current is obviously important, but we'll get back to that. So a 10 centimeter cube of quartz weighs roughly 2.6 kilograms or 6 pounds. Let's say due to the jostling of your fellow mosher, the impact velocity of your necklace is 1 meter per second. Stopping distance is 1 centimeter of sternum compression. That impact is 132.5 newtons of force. Spread over the 100 square centimeter face of your crystal, that gives us 13,250 pascals of stress. Assuming optimal axis alignment, that gives us a voltage spike of around 65 volts. Cool, you should be able to feel that. Unfortunately, the pulse duration would be low, so your brain might not be able to tell the difference between a shock and the physical thud of, a 6-pound necklace. Now, so far, we've been talking about you and your Coachella concert. But let's say that this video is really about how I want to die in a way that is so stupid and yet confounding that medical examiners far into the future will tell the tale. Ah, Sonny, I saw a lot of strange and tragic cases in my day, but none so initially mysterious and then incredibly stupid as the YouTuber that we found electrocuted next to a rock. Girls just want to live a life that people will remember. But I'm not like the other girls. I'm worse. They're all outside having fun in the sun, and I'm here inside with my sunglasses on, just... Anyways, okay, let's just say that I want to find a way to mysteriously die from piezoelectricity. I want to capture as much current as I can from the largest crystal I can by hitting it on something. At first I was thinking I could find like a giant shot put sized crystal and then like wrap a copper wire around it and then swing it around and hit it at something. To increase the current, I could cover both ends of the crystal in a conductive epoxy to try to capture as much of the surface charge as I can. But the thing I realized is that at some point, the crystal's just going to shatter. And if it shatters, that energy isn't converted into compressing the crystal. But then I thought, what if I put the crystal in a metal case, all except for the bottom face that will be exposed? At this point, it's way too heavy to swing around, but I could maybe pull it off the ledge of a building if it's balanced precariously, and have the bottom of the crystal hit the ground. The ground also, by the way, is covered by one of those industrial sheet road plates that they use during construction, and I'm standing on it with bare feet. And we're swapping out the quartz for some very specially crafted PZT. Millions of tiny wafers with a microscopic layer of superconductive platinum alloy. That's right, the wafers are in series. So I pull my 50-pound steel-jacketed, epoxy-coated PZT generator off a 3-story building, falling 10 meters and stopping in around 1 millimeter. So it hits the steel plate with an impact pressure of 220 megapascals. Does it electrocute me? Not quite. Assuming the electricity passes through me, the math says it has the potential to create a whopping 10 amps of current at over 1 million volts, but it only lasts for like 1/10 of a millisecond. If that pulse happened to hit my heart at the exact right millisecond of its beat, that could be fatal. But realistically, the pulse is far too short to reliably disrupt my heart rhythm. But even worse, I probably wouldn't even get shocked. Now, it is a common myth that electricity only favors the path of least resistance, because in reality, it takes all available paths. But it seems likely that the air gap breaks down into a superheated plasma arc, and that acts as a massive short circuit. That short draws so much immediate current that the generator's voltage instantly collapses. But okay, it seems like that arc of plasma would be really explosive and incredibly hot. Maybe it would burn me if I somehow managed to be in the path of it. Not exactly. In physics, temperature isn't everything. You also need total energy. So even if that plasma arc perfectly strikes me, the heat wouldn't fatally incinerate me. Instead, a fraction of those 2,000 joules will dump into a spot the size of a dime, potentially flash boiling the water inside my cells. Not even a full body burn. At this point, dying tangentially from piezoelectricity is getting harder than I thought. So okay, fine. Back to the drawing board. I swap the steel casing with tempered glass. I mount just the PZT on a non-conductive piston. I pull it down on the road plate. The piston shoots up, compressing just the PZT. The resulting 1 million volt internal arc blows the glass casing apart from the inside out. It doesn't electrocute me, but I do get hit with some high velocity glass shrapnel. I would have anyway, slightly later when the glass case itself hits the ground, but this was slightly earlier and with piezoelectricity, which is kind of cool, I guess. It's just not really worth it though. It's missing a certain je ne sais quoi, locked room mystery vibe compared to the secret electricity rock. It's fine. Now, I know a lot of you probably have even more crystal questions. Like, I'm an October baby, so tourmaline is the gem that I resonate with. Now, I have a pale tourmaline, but I need it to be deep red to match my color season. Really, a lot of common gem colors are not actually found in nature, and are created by irradiating gems. And, as we all know, you get deep red tourmaline with radiation. Duh. But, in the case of tourmaline, it is both piezo and piezoelectric. That means it generates a temporary voltage when heated or cooled. So, what are the implications of irradiating tourmaline? And that's a totally valid question. But first, it's time for the channel's first ever public service announcement. Do you plan to go to Coachella this year? Were you planning on wearing a giant piezoelectric crystal necklace and joining the mosh pit? Well, go for it. It's fine. Nothing will happen. So back to your question, what does happen when tourmaline is irradiated? Well, if the radiation is high enough, it will scramble the lattice, and the piezo and pyroelectric coefficients will drop, but it will just temporarily lose these properties. If the radiation is super high, like near a nuclear core, the tourmaline may amorphize, losing its lattice structure permanently and turning into glass. Actually though, in the gem industry, after irradiating topaz and tourmaline to change the color, the stones may actually have induced radioactivity. They may need need to be kept in lead-lined boxes for months until the radiation drops. So I guess don't wear your birthstone tourmaline until you know that it is no longer dangerously radioactive. In any case, I hope you've all learned something about crystals. The next time a mundane naysayer bursts into your edgy techno witch coven to say, "Your crystals do nothing," you can say, "Well, actually." I just want to say thanks for all of the help I got for this video. It started as back of the dingy diner napkin physics and turned into back of the crisp white envelope physics. My electrician neighbor, my physicist college friend, and my Patreon members all really did their best to help me figure out how to shock myself into the great beyond with piezoelectricity. And I couldn't be more appreciative. I also just want to thank this comment that gave me the idea for this video like a year ago. Bonus footnote. So when I crush the wintergreen candies, you're not actually seeing the electricity. Which you can tell because when I crush the tasty fruit candies, you don't see anything. What you're seeing is not actually the electricity. You're seeing the fluorescence that specifically only wintergreen candies have. Otherwise, I would have picked literally any other sucrose lattice containing candy. In both candies, the electric arc happens and nitrogen atoms in the atmosphere are hit by the electrons. These nitrogen atoms absorb the energy, become excited, and then release that energy in a burst of UV light. We can't see UV light, so we don't get to see the other tastier candies do this. But in wintergreen candies, the wintermint oil, methyl salicylate, actually absorbs the UV light and re-emits it as blue-green light. This is triboluminescence. Bonus footnote. So topaz is a bit confusing. The Curie brothers demonstrated its piezoelectricity, but based on its crystalline structure formula, it's centrosymmetric. So by definition, it can't be piezoelectric. So weird. It seems that the Curie's measurements may have been the result of crystal twinning. Based on what I could find though, these anomalies seem to actually be pretty common in topaz, so I left it because topaz would probably look prettier as a necklace. Patreon fact. Let's say you want to see something incredibly small, like at the level of molecules. Your most powerful light microscope won't work, because the objects you're trying to look at are actually smaller than the wavelengths of visible light itself. What if, instead of detecting light bouncing off atoms, you instead try to physically feel them by guiding the tip of a tiny needle over the surface and measuring the topography, like how people can read Braille. The needle is attached to a cantilever, which acts as a flexible microscope arm. This bends as the tip encounters tiny bumps and dips on the surface. To measure the tiny movements in the cantilever, a laser is bounced off the back, and even a slight movement in the tip causes the reflected laser to move significantly on the sensor. This is called atomic force microscopy and is used to create incredibly detailed 3D maps of surfaces at the nanoscale. This allows scientists to study DNA, how long polymer chains are, even individual atoms. What does this have to do with piezoelectricity? Well, you don't just have to drag the tip across. You can move it in the X, Y, and Z axes using a piezoelectric tube scanner. This is a tube of PZT with a continuous inner electrode and 4 segmented outer electrodes. When the electrodes apply voltage, the tube deforms, allowing the tip to move by fractions of a nanometer. It's like a tiny piezoelectric motor. My Patreon member Libby uses it to test how the stiffness of molecules from connective tissue changes from chemical modifications. Cells change their behavior in response to the stiffness of the connective tissue they sit on, often in ways that could promote the very disease that causes these molecules to become modified in the first place. The goal here is to identify whether these modifications could be a causative factor in accelerating disease progression. Neat. Yet another Patreon fact. True crystals, like the ones we discussed, have to have periodic arrangements of atoms, where the structural unit repeats exactly in 3 dimensions. 5-fold symmetry doesn't work in the lattice structure, and instead manifests as quasi-crystals. Their atomic structure is ordered, but they don't periodically repeat. As you can see in this, the most upsetting crystal image I've seen in a while. The longer you look, the worse it gets. Penrose tiling is the 2D analog, where 2 shapes can be used to tile a flat surface in a way that doesn't repeat. Final Patreon fact. There's piezoelectricity all around you, even inside you, even if you've managed not to eat the wintergreen mints. The piezoelectricity is in your bones. Your bones contain a kind of collagen that is piezoelectric. Now, collagen isn't a traditional mineral crystal. It's a liquid crystal polymer. But in the case of piezoelectricity, collagen uses large, flexible molecules as its building blocks instead of individual atoms to the same effect. You actually leverage the piezoelectric property of the collagen in your bones with mechanical loading, bone, such as exercise. This force creates electrical signals to guide osteoblasts to remodel the bone and increase its density. There's also been research to use heartbeats to compress piezoelectric crystals to power implants.